Okay, so in our last lecture, we finished talking about Huffman codes, right? And in particular, we talked about DRE Huffman code, right? How to determine the number of dummy variables or dummy nodes, and then we and then we talk about the optimality of Huffman code, right? So yeah, let's see what we cover exactly. And those are the procedure to code the DRE Huffman code, right? So we have a symbol k to denote the number of merges here, right? And then we can compute number of merges has to be bigger than this number, right? So yes.
Could you lower the projector screen?
Oh yeah, didn't do that. Oh, of course. Okay, so when you determine the number of merges first, right? If this number is if this number is an integer, then we're good, right? If it's not integer, we'll just take the ceiling of it. Okay, and then we know k, right? By knowing k, then we can compute the number of dummy nodes using this formula, right? And then we just assign probability of 0 to the dummy nodes, dummy nodes. Okay, and then after that, we'll just perform the merging algorithm of Huffman, right? So we rank the probability and then merge the least likely nodes into one node, and then we just keep doing that, and then we're good, right? So this is DRE Huffman code. It's pretty straightforward. And then we talk about the relation between, or discuss more on the Shannon code and the Huffman code, okay? And the Shannon code seems pretty optimal, right? Because we show the average length is very close to the entropy, and it will equal to entropy when the number of symbols goes to infinity, right? But we show that when n is very small and when the probability is very far from uniform, then the loss can be significant, right? So one example is this, right? If we consider a binary code, right, and then we code the probability of 0 is 0.999, and probability of 1 is this number, right? So they are very different, right? In this case, for Huffman code, we can just use 0 to code this guy and 1 to code this guy, and then right, the code length is 1, right? But if we use Shannon code, and you can see that for this small probability, we need to assign a lot of binary digits there, right? So this could be very suboptimal in this case, and then we show that Huffman code is actually optimal, right? It's not asymptotic, it's exactly optimal, right? When we consider zero error coding, exact zero error coding, right? And in order to show Huffman code is optimal, so we need to have the following argument, right? So here we assume the total number of source alphabet is capital N, right? And then we rank the probability in this way, right? And we denote Li as the covert length for the S symbol, right? And then so we have a mapping, so that's our encoder, right? And then this is the average code length, okay? The definition is the same as usual, right? And then we can show if the code is optimal, then we can show it has to satisfy the following three properties, right? It's called canonical codes, okay? The following three property is like, so we show the first one, and then from the first one, we can get the second one, and from the second one, we can get the third one, right? So this relationship, right? So let's say if the code is optimal, then for the probability pi is bigger than or equal to pj, then we know the code length will be li will be less than or equal to lj, right? So that's pretty intuitive, right? Because for a higher probability, then we're going to assign a smaller code length, right? The way to show that is by contradiction, right? So if this relation is not satisfied, then we just swap the code length, right? And then we can say, okay, by doing this, we can always reduce the average length of the code, okay? And then from here, we can show, okay, for the last two symbols, CM, CM minus 1, so those are the symbols with the least probabilities, right? For those guys, we know, so this guy, the length of this guy would be would be bigger than or equal to the length of this guy, right? But what we show here is that actually they have to equal, right? It's not bigger than or equal to, it's just equal, okay? So after this, and we can show that, okay, then it's possible that these two are siblings, okay? So it doesn't have to be siblings, but there always exists a code such that these two are siblings, okay? So yeah, the proof is pretty interesting. So if you don't recall, just look at our lecture notes for the proof. Okay, and then by knowing this, so what is really important is basically this guy, right? So we can know they have siblings, and also lengths of that equal, they're also important, right? And by using this theorem, so basically we can show, we can have two procedures, right? One is the merging extending procedure, and the other one is the reducing procedure, right? So here, basically, what we can do first is that, so this is our original code, right? So if we combine these two together and have a new probability here, right? So now we have a new source alphabet, right? And we assume that, so we have f prime, so that's optimal for the new alphabet, right? And then we can extend it or expand it from f prime to f, right? So we basically just append 0 to this guy to form this, and append 1 to this guy, to this guy to form f m, right? And then we keep all other code words the same. Then we can show that. So if f prime is optimal, then f is optimal. Okay, and this is very important, and we're going to use that to show why Huffman code is optimal. Okay, and the other way we can do it in another way, so which is that, so we can, if let's say f is optimal, right? F is for this probability distribution, right? I mean this, I mean the first one, right? And if f is optimal, and then we can combine the last two symbols all together, right? The probability of that together, and then we can have our f prime, right? The only difference here is that the last symbol of f prime is L prime, m minus 1. So that equals to Lm minus 1. Okay, and all other code words are the same. And then we can show that if f is prime, then if f is optimal, then f prime is also optimal. Right? So there are two procedures, right? So if f prime is optimal, we expand it, then f is optimal. And if f is optimal, and then we reduce it to f prime, then f prime is optimal. Okay? So we need both of those to show both of them are optimal, right? So the proof, again, is very tricky. Okay, so this is where we stopped in our last lecture. Any questions? All right. Today is our lecture number 22. And today we're going to finish talking about the optimality of a Huffman code. Okay, and then we're going to talk about a new code, right, which is a more modern code, right? In practice, we don't use Huffman code. Okay, so, but we use other kind of code. So, yeah, let's introduce you Shannon, Funnel. Yeah, probably you know these two names, right? Shannon and Funnel, right? Funnel's inequality, and also alias. Shannon, Funnel, alias coding. Okay, and this is one step closer to what we're using today, but it's still not what we're using. Okay, and yeah, probably let's say whether we have time or not. So next topic is that we're going to, after all of those, we're going to revisit Shannon codes. Yeah, the reason is that because we said in practice we can never know the exact probability distribution, right? So let's say if we do not know the exact probability distribution, then what is the loss? Okay, probably you can guess it already, right? We cannot mention that before. All right, so let's talk about the optimality of Huffman code. Yeah, and from our last statement, so think about how we can show the Huffman code is optimal, right? First, let's write down the theorem to tell you that Huffman code is optimal. Huffman coding is optimal. Okay, the meaning of optimal is that for a given probability distribution, PMF, the Huffman coding the Huffman procedure construct a NFG prefix code with minimum ln, right? So that's the meaning of Huffman coding. So the important thing here is that we can have this kind of code, right? Which means that for any n, right? If you give it n, so Huffman code is optimal, right? You cannot beat it. Okay, let's prove it. Okay, any idea how to prove it? Yeah, using what we just learned. Yeah, think a little bit, right? So I'll give you a hint, okay? So we're going to prove it by induction. Right? So normally when we prove it by induction, it basically means that for the simplest case, so it is pretty obvious that it is optimal. And then we're going to go from there using what we learned before, right? So let's go from the simplest case, right? So what is the simplest case? So, yeah. Say it again? K. Yeah, of course, right? Yeah, that's the simplest case. Can we go a bit further? Yeah. That mean if we only have one alphabet, then we don't need to code at all, right? So, yeah, the simplest case that where coding does needed is when the length of the alphabet should be 2, right? If the length of alphabet is 1, then what do you want to do with it, right? It always happen with probability 1, right? So the first interesting case or non-trivial case is that we consider the case where alphabet size is 2, okay? All right, so for the alphabet size 2, right? Yeah, let's consider the binary case, for example. Is this Huffman coding optimal? Yeah, it is, right? We only have 0 and 1, right? Yeah. We have to, the number of digits has to be integer, right? 1 is the smallest possible, okay? Because, here, n is 2 only, right? Not for, then, not n alphabet size, right? So in this case, Huffman coding use L1 equals to L2 equals to 1, right? Both of them only use 1 digit, okay? And in this case, it is clearly optimal. Okay, so yeah, then the base case is done, right? So now we're going to consider where m is bigger than, 2, right? So let's say m equals to 2. Okay, so by induction, so normally what we do is that we assume that we have an optimal code, or Huffman code is optimal for m minus 1, and then we're going to show it's also optimal for m, right? That's how it works, right? So what we do here is that we're assuming that we have an optimal code for m minus 1. Okay, and then we can construct an optimal code for m, right? And then we're done, right? Is that obvious? Or how can we construct it? So if we have an optimal code for m minus 1, and then how can we get a code for m that is optimal? Right, we just learned that, right? So from the last lecture, very last part, so we learned two procedures. One is expanding, and the other one is reducing. So what should I use here? Expanding, right? So expanding, basically, we can expand one more alphabet, right? So basically by expanding, and that's it, right? Because we show that if f prime is optimal, and then we expand it using the Huffman procedure, then f is also optimal. Okay, and then that's it. So yeah, that's how we show Huffman code is optimal. Okay, and one final word on this, right? So now we have learned Shannon code, and we have learned Huffman code, right? We have two codes here, and we know the code length. Let's denote the code length for Huffman as this. And then we have the code length for Shannon code. And we know Huffman code is optimal, right? Therefore, so for finite n, so this will be less than or equal to this, right? Okay, very good. And then, and what we have shown before is that, so the Shannon code is less than this, right? And this, obviously, that'll be bigger than or equal to this, and we show that, okay? And then if we compute the average code length, so it'll be 1 over n multiply this guy will be less than this. Okay, very good. So now let n goes to infinity, right? Yeah, let's assume a general, for example, let's assume it's a general stationary process here, right? If we let n goes to infinity, oh, so it means the 1 over n here, right? So this term will disappear, right? So what does this converge to for a stationary process?
Just entropy.
Entropy rate, right? So if it's IID, it's DMS, then it's just entropy, right? So just entropy rate, right? So basically, what we can say is that, so asymptotically, the performance of Huffman code will be the same as the performance of Shannon codes. And then that will be equals to the entropy rate. Okay, so this is entropy rate. In general. Okay, very good. Okay, so this is the Huffman code. Okay, we'll finish that. Okay, next, let's talk about another coding scheme. Shannon funnel alias coding. Okay, so before, how can I say that? So from now on, for this kind of code, we have a totally different coding idea. Okay, so let's see whether we can see that in a clear way or not. Okay. Okay, so let's write it down first. So what is the idea of this kind of code? Okay, so basically for this kind of code, based on the probability distribution, based on the PMF, so we're going to associate each of the source symbol to a point on the real line within 0 and 1. Okay, yeah, let's see whether that makes sense or not. Okay, so we're going to associate the source vector. Okay, so here we consider the block length is n, right? And we associate that to points on the unit interval 0 and 1. Okay. Yeah, because the point from 0 and 1, they are infinite, right? So we can deal with any n here. Okay, but the point is that, okay, so basically we're going to associate each point to a digit on 0 and 1, right? Obviously, we cannot use a real number to represent our code, right? Because that's infinite number of digits. Then we have to use finite number of digits there, right? We have to truncate them somehow, okay? So the key is how we can truncate them, okay? Okay, let's write it down. So then use truncation of the binary expansion of this point as code words. So this is the basic idea. So now let's see what is the binary expansion of this point, right? Because here let's consider binary code. We're going to use 0 and 1 to transmit that. So basically we're going to use a binary truncation, okay? Binary truncation means follows. So for example, let's say, so basically the number from 0 and 1, it's always 0 point something, right? So let's say the first, let's just say the first digit. So now it's a binary expansion, right? So usually we use 10, right? But now it's binary, then the first digit basically means what? Half, right? So for example, let's consider like say 0.0110110, right? The first digit basically means half, and second digit means half square, right? And then it means half third, 1/16, and here's 1/32, and so on, right? So this is basically the binary expansion, okay? And this is the number 0.01. You can see what's this number. You just need to add 1/4 plus 1/8 plus 1/16, and also these two numbers, add them together, right? So 1/64 and 1/128. Okay, so for example, let's say if we want to consider 1/3, so can you tell me what is the binary expansion of it, of this number? Right, if it's not for binary, it's decimal, then it'll be like 0.3333 all the time, right? But if it's binary, that'll be what? 0. For the first digit, it cannot be 1, right? Because it's less than half. That will be 0. And 1/4 is fine, right? So we have a 1 here, right? And for 1/8, right, we cannot have those. If we add them together, it'll be bigger, right? It'll be 0. And 1/16 is fine, right? And we'll just keep going it. It'll be 0, 1, 0, 1, 0, 1, and forever, right? So that's a binary expansion of 1/3. Does that make sense? Okay, so the reason we use, I mean, you can use whatever you want, right? It depends on what kind of code you have, right? Here we can just consider binary code, then we just use 0, 1, the binary expansion. Okay, is that clear? Okay, great. Okay, so now let's see what we're going to do, okay? Right, for example, let's say we have our alphabet is, let's say, A, B, C, and D here. And then we just use A is less than B, less than C, less than D here. So we call that, we can order them in lexicographic order. Okay, so this basically means that we just order them like A, B, C, D, or so. Okay, we can just order them. Yeah, the probability, the value of the probability doesn't matter too much. Okay, and then what we're going to do is as follows. So basically, after ordering it, so maybe, let's see an example here. So basically, we consider the probability of A is 1/3, probability of B is 1/3, and the probability of C is 1/8, and the probability of D is 5/24. Hopefully, the summation of them is 1. Okay, and we denote that as P1, P2, P3, and P4 here. Okay, so what we're going to do is as follows. So basically, let's consider a line here. So that's here's 0 and here's 1. Okay, so what we're going to do is as follows. So the first point we're going to get, we denote that F1 as F1. So that's the probability of P1. Okay, so here the value of this point is 1/3. Okay, and then the second value here, so we call that f2. So that is p1 plus p2. Okay, then that is 2/3, right? Okay, and then, yeah, it's horrible drawing. Yeah, let's redo this. Yeah, okay, yeah, 1/3 should be way big higher. Yeah, let's see, probably here is 1/3, here is 2/3, right? So here is f1, p1, and this is f2, p1 plus p2 equals to 2/3. Okay, and then you can guess, right? So what is f3? So that's p1 plus p2 plus p3. So that equals to 19/24. You can compute it. And then f4 is just 1. So that's p1 plus p3, 2 plus p3 and plus p4. Okay, and you can see that here fi is nothing but sum of j less than or equal to I and pj. Okay. So yeah, that's fi. Okay, so but that is not enough. Then basically we need to pick one point to represent each symbol, right? So those are not the point that we pick. So what we pick is the midpoint here, right? So the mid, yeah, let's use a different color. So what we use is the midpoint. So this point to represent the first symbol, and this point second symbol, and this point third symbol, and this point is the last one. Okay, so let's see. So can you tell me what's the value here, right? The first one is what? 1/6, right? Very good. And then we denote that as f bar 1. Okay. Then the second one is what? Half, right? Very good. So you just add this and that, divide by 2, right? And then similarly, you can compute the third one here is 35/48, and this one is f4 bar, so that is 43/48. Okay, so here we define fi bar, so as basically j less than I, we sum over all the pj, and then we add pi/2. Okay, that's f bar. So basically those numbers are used to represent our symbol, our source symbols. Okay, the first symbol is 1/6, second symbol is 1/2, and this symbol is 35 or whatever, and the last symbol. Okay. So the reason we want to do this is that we can make sure there's no overlapping. They are pretty well separated. Okay, so the next question, so we're going to show that later, so this could be a legit code. But one thing we need to determine is that, as we said, right, so basically, yeah, let's write it down. So the real number fi bar uniquely identify the i's source vector. Okay, so the next question is that how many digits or we need to use to represent each symbol, right? We need a truncation there, right? What is the length of the truncation, right? What is Li? Right, so basically what we do is that, so we need a truncation, right? So the truncation would be this guy, and then what we do is, because it's a truncation, right, we throw out some digit here. So therefore, it will be a lower bound. Or it will be a floor, but we only take Li digits of it, and Li is our coding length. Okay. So the question is, what is Li? So can you tell me what is Li? Based on what I've learned so far. Right, how do we determine the code length before?
Entropy.
The self-information, right? Almost entropy. So basically, this is what we do before. Right? But in this case, turns out that this is not enough. Okay. So basically, what we need is that we need to add 1 here. Right? So basically, the idea is that, okay, so now we want to code this point, right? So what we do not, maybe this is a good example. So what we do not want is that, after truncating it, which means we're going to make that smaller, right? We do not want to make it into this region, right? So we need to make sure this guy is bigger than this, okay? So this is not okay. Okay, we want to make sure that after the truncation, it moves something here, still within this region. Okay, in this case, in this way, then we know that every symbol would be, somewhere in this region, and then it's unique, right? It's a uniquely decodable code. Does that make any sense? Yeah, it's a pretty weird idea, but let's see. And basically, if we add 1 here, so we can make sure this can happen. If without this 1, then we cannot guarantee that. Therefore, you can see that for each length, so it's worse than Shannon code, right? Because we add 1 here. For Shannon code, we just have this ceiling, right? But here we add a 1 here, okay? The performance would be worse than the Shannon code. Okay, so now let's characterize what we just said, right? Let's characterize the truncation error to see whether this can be guaranteed. Okay, so basically what we're going to do is as follows. So let's use this guy minus this guy. So this is our truncation error. Okay. So basically, want to make sure the error has to be less than or equal to this guy minus this guy. Okay, and then we're good, right? So let's see. So first of all, we observe that, so this guy will be less than or equal to 2 power Li minus Li, right? Right, because the difference between this and that is just throw out some digit, right? The maximum, so this has to be less than or equal to this number, right? So if we add everything possible, in the maximum, it will be equal to this, right? So this is the highest number. Okay, and then let's see how can we upper bound this guy. So this guy equals to this. Oh. Right, and as usual, so we're going to get rid of the ceiling here, right? Okay, before that, we need to do one more step here. So let's take out this 1/2, right? So we have a minus here, so let's take out 1/2, and then we have this. Okay, and as usual, so let's get rid of the ceiling. So then we have upper bound, pi. Okay, right, and then we can see that, so this is nothing but half multiply pi. Right, okay, very good. And you can see here half would be very important. So we know this is less than this guy. And this guy, what is this guy? Right, let's see the definition here. So this guy defined by this plus this. right? Therefore, the difference, this guy will be just equal to the difference between this guy and this guy, right? So that is basically this minus that, right? Here is f bar 2, and this is f1, okay? And then we can show that, okay, the truncating error is totally okay. Okay, we're not so bad, so we can make sure that, so this point after truncation is bigger than this, okay? And by this inequality. All right, so then we could conclude that, so this guy, bar Li, so that is in the region between this and that, right? Then this basically means that, every code word will be in a unique region, right? Interval, right? And then, so this can be used to uniquely represent the source vector. All right, very good. Okay, I have 10 minutes, then let's show the following theorem. Okay, so the only thing now we need to show is that, so this code word is a prefix code, okay? Theorem. So we let 0.b1, b2 up to bli be the binary expansion of the point this Li. Okay, then we say the code words satisfy the prefix condition, meaning none of the code word is a prefix of another one. Okay. If the interval 0.b1, b2, bli, and 0.b1 up to bli plus 2 power li. Okay, so if the code are prefix, then this would be disjoint. If these are disjoint. So basically, we can show that if those are disjoint, then we can have a prefix code. Okay, so let's see how we can prove that. Yeah, the proof of it is by contradiction. Okay, so basically we assume the code is not a prefix code, meaning some code word is a prefix of another one, and we're going to see those will not be disjoint. Does that make sense? Okay, so let's assume that, suppose that the C is a prefix of C prime. Okay, C is a prefix of some other code word. Okay, and then we can see, let's assume that, okay, then, so the C prime, so can be represented by, so here is a C, 0. So here is C, right? But since C is a prefix of that and they're not the same, so we have to have some C double prime here. Okay? And C double prime cannot be 0. Sorry, cannot be empty. Okay? Right? And from here, we can see that the value of C prime, 0. C prime, has to be bigger than the value of C, 0 point C, right? Because we have additional C prime, double prime here, right? So this code is a prefix of another one, right? And another thing we can observe here is that, so 0 point C prime, okay, that will be less than 0 point C at 2 power LC, right? Because C prime is this guy, right? 0 point C is this guy, right? If, we have all the largest value, from now on to infinity, and then if we add them all together, it'll be this number, right? So then we have this. It's geometric theories. Okay, great. And from here, we can conclude that the value of 0 point C prime is bigger than 0 point C and less than 0 point C plus this guy. What does that mean? Or we can see, what is this? Right, that's exactly this. Right, so this is C, and this is C plus 2 power, there's a minus sign here, minus Li. Right, that's exactly this interval. Okay, so if one is a prefix of another one, so we can see that C prime is in the interval of C. Okay, then we have a contradiction. Right, because we assume that all to this are all disjoint, right? Okay, then from here we can see that, so basically the Shannon, this code is prefix code, right? Any questions? Okay, great. So now let's characterize the average length of this code. Average length of Shannon funnel alias code. Okay, so basically, as usual, so our computation is like this. From 1 to n pi times li, right? So that's equals to summation of all x. So we have this. Then we multiply the code length, right? Code length, as we said before. So this is px plus 1, right? And then we can see this is less than or equal to px. And we get rid of the ceiling, right? And then we can add 1 and add another 1 here, right? Because so this guy is less than or equal to this guy, right? And then we have minus this log px, and then add 2, and then the first term is nothing but our entropy, right? We'll assume a DMS, right? Let's assume. And then add 2. Okay, and we use the DMS property here. Okay, and for Shannon code, we only have a +1 here, right? Here's +2. Asymptotically, it is still optimal, but we do lose something here, right? So it's not as good as Shannon code in terms of the average code length, right? So then the question is why we want it, right? Why we want this code? Can you think of a reason? You can see that the designing idea for this code is very different from before. right? For Huffman code, we need to compute all the code words, right? For Shannon code, we need to compute the length, and then we need to compute all the code words, right? Using a construction tree, right? For Huffman code, also we need to do this Huffman procedure to have all the code words, and then store all the code words into our memory, right? And when we do the encoding, we just look it up and then find the corresponding code word. Okay, this is how we use the Shannon code and how we use Huffman code, right? But for this code, do we need to do that? Do we need to compute all the code word beforehand and store them somewhere? We don't, right? Because you can see, so each code word is obtained from computation, right? If we know the probability, then we could compute the digit, right? And then truncate the digit and then transmit. So we do not need to store the code book. Does that make sense? Right? So we don't need a code book. Okay? So the code words can be computed online. Okay? So this is one huge benefit, right? Think about when n is extremely large. In practice, n is like more than 1,000. Okay, so I mean it could be much larger than that, right? So it's a huge benefit if we do that, right? And then correspondingly, what are the drawbacks? Okay, the same thing, right? So because we need to computing the code word online each time, right? If n is extremely large, right, we need to compute the probability first and then truncate. So this could be quite cumbersome. Okay, so constructing or computing this guy for large n is impractical. At least it is impractical back then, right? Okay, then how can we solve the problem? Right? Yes.
But like the first part, like the advantage of the code book.
Uh-huh.
So like we're just computing it based on like
Probability,
you transmit
PMF.
just like the distance measured that by, and then you like turn that to like the binary truncation. That's just a code word.
Exactly. Exactly. Right? So, but now the cumbersome thing is that, so the n could be very large, right? And then we need to compute that for the whole block, right? And in practice, right, n could be, let's say, if you want to transmit a book, right? So can we think the entire book as a block and then transmit? So that would be very impractical, right? Then what should we do in practice?
Just create smaller blocks.
Yeah, that's one way to do it, right? But then you're gonna lose something, right? Because for this, the big thing for this book is that, so we have worse performance here, right? Okay, so basically what we do is that, so this guy can be constructed sequentially, step by step, okay, by considering the sequence of source symbols x1, x2 up to xn, and so on. So we can do that sequentially. So basically, if we observe x1, we just encode it, right? And based on that, we'll do another encoding, x2, and again. Does that make sense? Probably not too much, right? So basically what we do in practice is that, okay, so from the beginning we have from 0 to 1, right? And then we have some interval. For example, we have some interval let's say, to represent P1, okay? And this is for symbol 1, right? And then for the next symbol, so we consider this interval again as a whole interval, right? And then maybe add another point here. So that will be the encoding of next symbol, right? And then we consider this interval again, right? And then maybe next time is consider this symbol and make smaller. And then basically we consider sequential coding of it, okay? The exact procedure is very complicated, and I don't think we can make it right by hands. So, but this idea is called arithmetic coding. Okay. And if you're interested, just take a look at detail of it, right? So this is, the idea is from the Shannon funnel alias coding, right? And this is what we use today. So it's a practical coding, right? So for example, for image processing, for image coding or JPEG or JPEG 2000, we do use arithmetic coding like this, okay? So consider them as a sequence. Okay, but this is not required in our class. So you don't have to do this by hand, but just, I think the concept is pretty interesting. All right, okay, so I think that'll be it for today. So yeah, I'll see you in next lecture. Thank you.